Before we jump right into this proof, one thing we'd like to do is explore a little bit first and look for why this might even be a good way to try to prove what we're looking at. Because we definitely believe that the Pythagorean theorem is true because we've heard it said to us a bunch of times and because we've seen a lot of examples. But why is this a good way to prove that? The diagram that you're going to see, that you may have seen reading the book, or that we're going to use for the next proof doesn't seem at first like it has anything to do with what we're talking about, so let's explore for a moment. So what I've got here is that diagram we built in GeoGebra. I added labels for the sides, and I've manipulated this around to be our good friend, the 3, 4, 5 triangle, just so that the arithmetic, as we're exploring this, will be pretty easy. So what I'm going to do is look at ways of cutting up the c squared square so that it makes two pieces that are consistent in size, if not shape, with the other two squares. So I'm going to just drop a point in there, and I'm going to say, okay, let's try drawing a line parallel to one of the edges through that point. Well, that's going to give us a couple more intersections we can use. Whoops, that's a little bit off. Come on now. Okay, it doesn't like Control Z. That's still a little bit off. Right there. Okay, on the intersection. Good GeoGebra. Sometimes you have to talk to it. It's like any computer program. Okay, so how are we going to use that to help us out? Well, what I'm going to do is draw polygons overlapping that square. So clearly, these two rectangles together are adding up to the same area as c squared. And we can see the area of each of them by using the area measurement tool. What we want to know is how we can cut that square up in such a way as to be consistent with the other two squares, 9 and 16. So what we can do is drag this point around until we hit the right spot. So let's see. We can get pretty close to 9 and 16 here, and we know it might be a little off because of just pixel by pixel rounding errors. This point, is that the midpoint there? Let's take a look. So let's see, in the construction tools, I know there's a midpoint one. Yeah, there we go, midpoint or center. It's kind of close to the midpoint, but not exactly. And in fact, if I drag so that that's intersecting even closer to the midpoint, it looks like it's even more off. Okay, so that's not going to help us. So that's fine. We found one thing that won't work. So let's try the other way of cutting this up and get as close to 9 and 16 as we can. Okay, I've gone past, so I'm going to zoom in to try to get that closer. I know I might not be able to get it perfect because of pixels, but, we should be able to see what's going on. Okay, and I actually got it right onto 9 and 16, so that was cool. And it looks a whole lot like it's going through this vertex right here, so the right-angled corner. So that's the idea I'm going to carry forward into the actual proof.